So I would like to thank the organizers for the invitation to speak here. So I will talk about some joint work with Vaughan Jones, Dimash Otenko, and Paul Justin about the POTS model on random graphs, loop models on random graphs too, and the relation with random matrices. So this is also related to some work with Edouard Morel-Segala, and because I was not sure that the Blackboard would be so nice, I prepared some slides in case, and you can find them on my website. So the name of the file is just pots Saint-Petersbourg.pdf. Maybe. So the topic of this, is it okay with the sound? Yeah. The topic of this work is about the relations between some statistical models on random graphs, and more precisely, as we shall see, on maps and random matrices. So this topic goes back to the 70s with some work of Taft, who found out that if you compute some matrix integrals, then you can see them as generating function for the enumeration of graphs which are sorted by their genus. And this remark became a whole subject in theoretical physics. So there was this important work by Brezin, Parisi, Itzikson, and Zuber. So in the 78, we showed how to compute the number of certain graphs sorted by their genera by using matrix integral. And since then, I mean, there have been lots of generalization of this work. So there are people working in this area like Kostov, Kazakov. So if I think first about Russian people, Chekhov, for instance, you can think about so Paul Justin over there, or Bertrand Hénard, who is very active in this field and is trying to show that somehow most problems, lots of problems, can be rephrased in terms of matrix integrals. So in this mini course, I will focus on a very specific model, that is the POTS model. And I will try to show you how this is related with random matrices, and eventually how this relation can be used to compute things. So if you compare to the talk of Hugo and Vincent, I will consider also the POTS model, but somehow my POTS model will not be on Z2, but I will make some summation over graphs, so it will be on random graphs. And I will try to do actually a bit more precise thing than what they're doing, in the sense that I will try to compute the partition function. And this by the use of these random matrices. So today, I will just show the relation. So it's really much like in Vincent's talk, relation with the loop model, so that it is clear the kind of problems I will be dealing with, and the enumeration of maps. So I will tell you what is maps. The next lecture, I will, or maybe I will have some time to start this today. I will show you how this is related with random matrices. And the last lecture will be somehow to show how to compute the partition function well, compute is always a big word, the partition function from this relation. Okay. So this will be more or less what I am thinking to talk about. Maybe you could have noticed that one of the co-authors is Vaughan Jones, who is more known about his result on subfactor theory or knots theory than in statistical mechanics. And the point is that this area is also related with subfactor theory on planar algebra. But I will not, so in this course I will not talk about it. The only point will be somehow that what the construction that Vaughan did in subfactor theory will be used to construct the right random matrix model. But you don't need to know anything about planar algebra or subfactor to follow what I will do. So it will just give you maybe some, and if there is a big demand so that I talk about this more, I can try to do it in the last course. But okay, we will see. Okay, so today I will just try to make this relation between Potts model and the loop models clear. And so I will go back to this duality that Vincent talked about on how to transform the problem of analyzing the Potts model to a problem of analyzing a loop model. Okay? So the Potts model is given. So Hugo and Vincent described it through the probability, and I will rather consider the partition function, but this is always pretty much related. So I take a graph, VE, and I look at the summation over, so the configuration, and I take a weight exponential beta times the sum over ij, which are edges of G, so ij are vertices, and I put a contribution if two neighbors have the same color. Okay? So, oops. Okay, this was not very. Okay, so now I want to transform it into a loop model. So the first step is to transform it somehow into a cluster model. Okay, so what you do, one way to do that is so to see that as a product on ij in V, so maybe the edge in E, times exponential beta minus 1 that the color of sigma I is the color of sigma j plus 1. And then you expand this. So this will be the sum over the sigma I. And you expand it about the subset of edges in E, such that, so if I call this V, I have V times the number of edges in E prime times the indicator function that all the spins in E prime have the same color. Oops. Okay, and once you have done this, you can make the summation about all the possible configurations of the spins. So what you see is that if you want to make this summation over there, you have a constraint that on the vertices which are related by the edges in E prime, you must have the same color. Okay, so if you let cluster be the sets of vertices connected by edges in E prime, then what you see that your partition function that you want to compute is given by the sum of E prime inside E of V times the number of edge in E prime times Q to the number of clusters. Okay, so here let me give an example. So for instance, if you're, so I will try to take always the same example of graph. So this is G. And so if E prime is something like this, then what you see is that for the number of edges in E prime is 4, 1, 2, 3, 4. And the number of clusters, so you have one here, and you have one vertex here which is alone. Okay, so the number of clusters will be 3. Oops. Okay, so now I want to transform this, but I want to take, at this point, random graphs. So what I will do, I will sum over graphs which are planar. Yes? Okay, sorry, I thought you. I will sum over graphs which are planar. More precisely about, I will sum this partition function over rooted planar maps. Planar maps. Okay, so what is a map? So a map is a connected graph which is embedded or drawn on a surface and it has a genus. So this means properly embedded, I mean. So this means you want to draw your graph on a surface so that the edges of this graph will not intersect on this surface. Okay? Edges do not cross. So the genus of the map is the minimal genus of such a surface. And you have actually, if you look at a graph, you can say what is the genus of the map. So you have this Euler formula that also Vincent alluded to, which tell you that 2 minus 2g, so the genus is g, is given by the number of vertices plus the number of faces minus the number of edges. So what are the faces? The faces are this portion of the surface which are limited by the edges of the graph. Okay, so they are homomorphic to a disk. Okay, and the last thing so I have to define is the root. So it means that there is an oriented graph, an oriented edge which is distinguished. Okay, so for instance, if you look at this, I have how many vertices? I have 1, 2, 3, 4, 5, 6. And number of edges 1, 2, 3, 4, 5, 6, 7, 8. And number of faces, I have 1, 2, 3, 4 on the external face. So it's 5. So the difference should be equal to 2 so that I have genus 0. And let's see. So I have to do number of what? Edges. Oh, that's the problem when you start trying to do things that you didn't think about before. Okay. And so the difference is okay? Yes? The genus should be 0. Okay. Okay, so and so a root would be something like this. You're just given a rooted oriented edge. Okay, and now what I want to consider is this model, but where I sum the partition function over all these rooted graphs, and I can put some weight over the number of edges and vertices. So okay, so I want to consider the partition function. So Potts model on random graph. So it will be on random planar maps, actually. So you take Z, so beta Q, which is the sum, well actually it should be also with two other parameters. So G, so in this rooted planar maps, and you take some X to the number of edges, Y to the number of vertices, and then you sum this Z of G, beta Q. And you can consider also, if you want, the law and the configuration which has this partition function. Okay? So what I want to show you now is that this can be rewritten as the sum over planar maps with vertices with valence 4. And I will have some delta to the number of loops, alpha to the number of some vertices of type 1, and beta to some number of vertices of type 2. Okay, so this is somehow what I aim to. And to do that, I shall use, like Vincent, this dual graph and also another graph, which is in bijection, which is the medial graph. Okay, so this is a question mark. Okay, I'm going to show you how to do that. And okay, so remember, so I have my graph. I have my graph, and I want to define two other type of graphs. So as Vincent, I have my dual graph. So this is my graph G. This will be my dual graph. So the vertices of the dual graph are placed in the middle of the faces, and you have edges orthogonal to each and here I should also have one like this. Okay, so this is a dual graph. So each edge has another edge which is which intersect it in the dual graph, and each face is given a vertex. So you have this external face. And now I'm going to, and this is clear that this is a bijection. Okay, being given the dual graph, you can redo the same. And in each face of the dual graph, you have a vertex, and you can draw your dual graph. And so you have another graph which can be associated to this graph, which is a medial graph. So this will be medial. And so the edges of the vertices of the medial graph will just be given by the intersection of the edges of the dual graph and the edges of the graph you started with. And what you can see that the faces which are limited by the graph and the dual graph have always exactly two edges from this graph, just because this will have only one boundary which is from the original graph, one connected boundary, and one connected boundary from the dual graph. So you can, in each of these faces, you can draw an edge of the medial graph. Okay? So this is always difficult. Okay. Okay. At the end, you should see that the medial graph has vertices which are four valent. Okay, from each vertex, you have exactly four edges going out. I missed one?
Yes. Another one.
And to the right.
Another one.
Yeah.
That's why I wanted to do slides, you know. Well, yes, here. Yes.
To the top of it.
To the top of it. Okay, great. Thank you. Okay, so, and you can see that, so for the medial graph, if you have just given the medial graph, you cannot really distinguish between the dual graph and the original graph. But if you are given a color, let's say if you are told that this one, you have a vertex from your original graph, you can remark that the whole graph is kind of bicolored. I mean, this will have vertices from the dual graph, this will have vertices from the original graph, and so on. So if you would color, maybe I could try to do that. So you could color this in a checkerboard way. So if you give yourself the coloring, then from the medial graph you can recover, on this coloring, you can recover your original graph. Okay? And actually it's enough to give you one color because then everything will be colored. Okay, so now I'm going to try to do for you the configuration. Okay, so remember, so we have this configuration coming from here. So here it's in red, but now I have not enough color, so I will just double them. Okay, so this was my configuration. So if I come back to here, this was my edges in E prime. So how being given the configuration on the major graph, how can I match this configuration? So here the way is for the dual graph is as what Vincent said. For the dual graph, what you do is that you take as bonds all the edges which intersect an edge which is not a bond in E prime. Okay, so this will be like this. Okay, so let's see. Okay, I'm sure I'm going to miss some. It looks like okay. Okay, so this is the configuration on the dual. And again, you can find your configuration on the dual by the configuration on the you can find the configuration on the original graph. So there is a bijection. So now how do you define a configuration on the major graph, which is in bijection with the configuration on the original graph? What you do is that you split your vertices. Okay, so that they do not intersect bonds in the dual or in the original graph. So typically, here you are going to split it. Here you are going to split it. Here, so here you are going to split it like this because this was a. Okay, and here you are going to split it like this. So I certainly forgot some. Here you are going to split it like this. Here you are going to split it like this. Okay, so at the end, what you get is a configuration of loops. I mean, the major graph gives rise to loops. So here I forgot to do that. And this is, so this will be somehow what will give rise to this loop model. Okay? So now what we would like to do is to express. Okay, so is it clear how I did the configuration of the major graph? So you just split the vertices like this, so that they become either this or this. So that somehow they never intersect the bonds in the dual or the original graph. Okay, so now what we want to do is to get this formula. And there is a useful formula to get from here to the sum of our loops, which is what I think at some point Vincent used, which is if you look, so the lemma will be that, so if you look at the number of clusters in the original model, then this will be the number of vertices plus the number of loops and minus the number of bonds. And how do you prove this formula? So what you do is that you write in each of the clusters of the original graph, E prime, you write the Euler formula. So the proof is that on each cluster, what you find is that you have 2 by Euler formula, which will be the number of vertices plus the number of faces minus the number of bonds in this cluster. So when you sum it, what you get is 2 times the number of clusters, which is going to be given by the total number of vertices in E, since all the clusters cover the whole graph. And here the point is to see that the number of faces, when you sum over all clusters, this gives you exactly the number of loops. Indeed, you can see that you have a loop inside each face, and all the remaining loops are just the external face of your clusters. So when you do that, you have plus the number of loops and minus the total number of bonds. Okay, so if you come back here, what you get is a sum over G, x to the number of edges, so y to the number of vertices, and then you have the sum over the configuration E prime in E of, so it was V to the number of bonds, Q to the number of clusters. Okay, and then you use this formula to get rid of the clusters inside this sum, and what you will get is the sum over, so you have to see how to express the number of edges and bonds in terms of this loop model. So what you will keep is the vertices of your medial graph. So you see you have two types of vertices. You have this type 1 and this type 2, V1 and V2. Okay, so if you look at the total number of vertices V1 plus the total number of vertices V2, this is exactly the number of edges. And if you look at the number of vertices V1, this is exactly the number of bonds. Okay? So now if you put these two formulas into this formula, what you will get is the sum over the vertices. So you will have square root of Q times the number of loops. And you will have alpha to the number of vertices of type V1, beta to the number of vertices of type V2, and times, so y square root of Q times the number of vertices of the graph. Okay, and here alpha, so alpha should just be x. So V1 and beta should just be x, and alpha should be just square root of, so this should be square root of Q. Let me check I didn't make a mistake. So it should be x V divided by square root of Q. Okay, so I'm just changing the variable, and I see that all these three terms are just, yes?
The letter beta, isn't it overcharged?
Ah, yes, you are right. It's not a good name. Okay, so let me keep x.
X, Z, X, Y. X is
There is already X there.
You already know.
No, it's the same. Okay, so I just write edges. The number of edges as the number of vertices of type V1 plus V2. So I have x to the V1 plus V2, x to the V1 plus V2, This is V to the V1. Well, it's not a great notation. Okay. And this is square root of Q times this thing. Number of vertices minus number of loops, which is the number of vertices of type V1, minus the number of minus the number of V1 minus the number of loops. Plus the number of loops. Okay, I'm just using this. And I think this is, so I will get x to the V2 by here, and otherwise I have only terms in V1. And it should be something like this. Okay?
And square root comes from
the 2. Yeah. Yeah. Okay, I think I'm more or less where I want it to be. So I don't like this term because this term depends on the number of vertices of the original graph. So if you take it equal to 1, then you get the loop model that we can analyze by matrix integrals. Okay, so what I have done for you is show you how to relate the partition function on the original graphs to the a sum over, so what do I sum on? I sum on these medial graphs, so which are 4 valent maps, planar maps, that you build over vertices of this type and vertices of this type, and you count the number of loops. Okay, so let me recast where we arrive. So what I did is just show you that if you take a special parameter in your original partition function, so you can see Z. So Z for y, which is 1 over square root of Q, you can see that as a generating function so a generating function in terms that you have these 3 parameters, and if you sum over all planar maps, so you will count the number of 4 valent, so rooted. Actually, I didn't say it, but it's clear that if you give you a root on the original graph, you can also give you a root on the dual graph and a root on the medial graph. So it's the 4 valent rooted planar maps that you can build with, so what? So you will be given a number V1, so N1 of vertices, so which corresponds to the bonds. So this will be the vertices which correspond to the bonds. A number N2 of vertices corresponding to the other coloring, so the dual graph. And you will be given a number P of loops. Okay, so if you think about the problem of computing this partition function, if you want to compute it for a continuum of values of Q, alpha, and X, then this is exactly the same as being able to count the number of possible matching of, so if you are given these vertices, maybe I should do it here. Okay, so So this is the same. So this means that you are given yourself these vertices. So you have two types of coloring. So this I think about it as vertices. So let's imagine, so I have some coloring inside. And let's say I have two like this, which corresponded to bonds. And this means that here I have some red. This means I have something coming from the dual. And let's say here I have some vertices corresponding to edges in the dual in the middle. Okay, and you ask yourself, if I draw these vertices, and let's say that there is one root, if I draw these vertices, how many planar maps can I draw by matching the endpoints of these vertices so that the colors are the same? Because remember that, I mean, it's just, so let's see, so something like this. So let's see if I can do it. Okay, so how many possibilities do I have to match? Let's see, these endpoints. So what happened here? Okay. Okay, so how many such configuration can I have? I mean, it's not an easy problem, and actually it was solved on a combinatorial fashion only very recently by Bousquet-Melou and Bernardi. And what I will try to show you is how to do that using random matrices. In the rest of this, this course, well, today, I would like to show you just the simplest model which was tackled by Brezin, Parisi, Tsingson, and Zuber. So the problem that they ask is exactly the same, but without any coloring, any configuration inside these vertices. So the question is, okay, so the simpler question so imagine just you are given these vertices, but you don't know what is inside and you don't care. So how many, and you are given a root. So how many possible matching do I have so that the resulting graph is a planar map? Let's see. Oop. So it's always a bit. Okay. So the question is how many matching so that you get a planar map. Okay, so if you think that inside of these vertices you have square, what you are asking is how many quadrangulation of the sphere you can make with this given number of patches, of squares. So this question was tackled already, so in the 60s, I think it was 62 by Tutt, who could solve it when you have a quadrangulation or a triangulation. And then, so this was what Brezin, Parisi, Tsingson also solved. Brezin, Parisi, Tsingson, and Zuber. solved in the 78 by using matrix integrals. So before the end, I would just like to say how did Tutt could solve this kind of question, because somehow we will see that this will come back in the analysis of the approach by random matrices. And the main idea so actually I can tell you Tutt theorem is that the number above, I don't know it by heart, but this number, so number with n vertices, rooted quadrangulation with n vertices. So this is given by 2 over n plus 2, 3 to the n, n plus 1, 2 to the n, n. Okay, so he got really an exact formula for this question. And the basic idea that Tutt had was to do some surgery. So basic idea. So do surgery on maps. So namely, you let A PL to be the number of quadrangulation, well, of planar maps with, so P vertices of degree 4 and 1 of degree L of degree L. And so the idea is that you can perform some induction on this number, find some induction relation, which you can eventually solve. Okay, so you can represent this as having all these 4 valent vertices, and then you have one with L edges, and you have a root. Okay, and what you can do is to look what will happen with the root. Okay, so the root can either be matched with one of the 4 valent vertices, or it can be matched with itself. Okay, and so this gives you, so what is that? Once you have matched the 2 half edges, you can somehow contract it to get rid of it, because it will not play any role anymore. So this is a number, so you have one vertex less, and this one will have gained 2 additional edges. And this one, so you see you're splitting, because you have a planar drawing, you are splitting the enumeration in 2 disjoint parts. I mean, the 4 valent vertices which will be in this part will never be matched with the vertices in this part. So you see that this will be the number of a possible choice, so of your 4 valent vertices to be here or here. So it's k equal to 0 to p. And then you have to choose a number of vertices here. So it will be n equal to 0 to L minus 2. And then you have a product A of, so K n, A L minus K, and n minus P minus K, yes, and L minus 2 minus n. Okay, so by doing this simple surgery, the simple induction over the additional vertex, you see that you get some induction relation which actually defines you uniquely your numbers, because you know what is the numbers where when P and L is 0, and so this gives you some induction relation which allow you to compute actually your numbers. But it's not easy from this induction relation actually to get the exact formula for this enumeration problem. Okay, so this is really also what Tut had to do. I wanted to show you this proof because what we will see later is that when you use matrix integral, the main tools to analyze loop matrix integrals is what is called loop equations. And these loop equations are exactly of this type. And actually, you can relate all the enumeration problem, this type of enumeration problem with random matrices by simply using this kind of induction relation, which are the same in both cases. And this is actually also what physicists like Bertrand and I are doing, is showing that somehow two things are the same because they satisfy the same induction relation. So I don't know if I'm supposed to end up in advance or maybe not. So I can maybe start on a little on what will be the next course. I can announce in 5 minutes. So maybe, so the next course I will start going on random matrices. And how do you relate? So how do you relate? So how are random matrices related to this questions? So the first answer, the first point which is important is the notion of Feynman diagrams. So what are Feynman diagrams? It's a way to compute Gaussian integrals. Okay. And on what is it based? It is based on Wick formula. And Wick formula tells you what? So if you take G to be a standard Gaussian variable, say with variance 1, then you can compute the moments of this Gaussian variable. Well, actually, you should better take 2n, otherwise it will vanish. And you can see that this is the number of partition of 2 endpoints per partitions. Okay, so this is a number of pair partitions. So you can see already that the expectation of a random variable can have some interpretation in terms of combinatorics. And actually, I can give you as an exercise to prove this by using integration by parts. Okay. It's a way I like to prove this because this is somehow what we will massively do later on which is related with this kind of equations. And now what we will see in next course, and we will elaborate quite a lot on this, is that if we take so-called matrix from the GUE, so xn n times n matrix from GUE. So this means, so I will come back on it next time, but this means that you have a matrix which is self-adjoint with complex entries and with Gaussian entries. So this means that the xn ij are going to be some complex Gaussian divided by square root of 2n. So outside the diagonal, so Gig and G tilde ig are just standard real Gaussian variable. And so what we will see next time is that if you compute moments so if you compute moments xn, sorry. So this will be the sum over the genus 1 over n to the 2g times the number of planar maps. Maps with genus G built over one vertex with valence 2p. Okay, so this will be as a start of next time. So what we will see is that if you don't look at a one-dimensional Gaussian, but if you put all your Gaussian variable inside a big matrix, then the moments will be given as some generating function of the number of maps. So graphs which are this time sorted by their genus. Okay, so here, this case is a special case with n equal to 1. But you see that adding the dimension allows you to separate the genus, and in particular in the larger n limit, what you get is only planar graphs. So elaborating on this, what we will show is that making this expectation more complicated and considering more complicated things here allows you to, in fact, have this kind of result, but here you have the partition function of the Potts model. So this will be the goal next time. Thank you very much.